Good morning, dear participants, and welcome to this first session of day 2 of this faculty development program on computer techniques in engineering. I welcome you all this day 2. For the first session, I hand over to my colleague, Dr. Pankaj Tyagi, who is an assistant professor at the University Polytechnic, to moderate this session. Mr. Pankaj Tyagi, please.
Thank you, sir. Very good morning and assalamu alaikum to one and all present on board. I, Pankaj Kumar Tyagi, on behalf of the organizing team, would like to extend a warm, gracious and inclusive welcome to the distinguished participants of this Atal FDP on session 1, day 2. It's my privilege to introduce the esteemed session speaker for this session, Professor Dr. Fasial Hasan. Dr. Fasial Hasan is presently working as the professor in the Department of Mechanical Engineering at ZH College of Engineering and Technology, Aligarh Muslim University. Dr. Hasan obtained his Ph.D. degree in Reconfigurable Manufacturing Systems from IIT Roorkee. He joined the Mechanical Engineering Department, AMU Aligarh, in the year 2003. Dr. Hasan has more than 100 papers to his credit, research publications, including books chapters, and research articles and conferences and journals of high repute. Dr. Hasan has supervised more than 5 PhDs and 15 dissertation projects. He has 2 patents to his credit, and he is among in the elite group of highly cited authors. Dr. Hasan has also served as the resource person in more than 20 invited talks at different conferences at different premier institutions. He also acted as a resource person and simultaneously the editorial board members and the reviewers in the different journals of high international repute. He is the members of many professional bodies, including the Agronomic Society of India. Apart from his academic credentials, Dr. Fasial Hasan has also rendered a large number of administrative responsibilities at Aligarh Muslim University, Aligarh. To mention a few, he the OSD to the control of examinations. He has also served as the coordinator of PhD programs. He's also served as the assistant director at the Directorate of School Education, Aligarh Muslim University, Aligarh, as the assistant superintendent exams, and the warden at different halls of residence. With this brief introduction, I would like to request Dr. Fasial Hasan to address this august gathering on a very pertinent topic, modeling using genetic algorithm. Over to you, Dr. Fasial Hasan, sir.
Thank you, Dr. Pankaj. So a very warm good morning to all the participants and the organizers. So before starting, I would just like to thank the organizers for giving me this opportunity to present some of my ideas before you. So not wasting much time, straight away, I'm sharing my presentation with you. So I think my presentation is visible to all of you.
Yes, it is visible. Yeah.
Okay. So Dr. Pankaj has already told that I will be discussing something about optimization using a relatively new class of algorithms, what we call as genetic algorithms or evolutionary algorithms. So in this presentation, I will be giving you a brief introduction of what optimization is all about, then a detailed overview of genetic algorithms, what are the important parameters, and in between, while discussing the algorithms and the parameters, I'll explaining you these concepts with the help of some examples. Okay, so this will be my presentation outline. Now, let us first see what do we mean by optimization? So just to explain, say for example, if you have a starting point, say S, and you have a destination, say D. So from a starting point or from source to destination, you have n number of routes. Now at times you prefer route 1, at times you prefer route 2. Here the pertinent question is on what basis you are deciding upon the route. So if anyone can answer why we are deciding this route, then the concept of optimization can easily be explained. So the thing is that at times we decide route on the basis of road condition. Another point of time, we may decide the route depending upon the congestion. At times, we decide upon the route that how many number of tolls we will be coming across. So these are the different criteria on the basis of which we decide upon which route we will prefer over the other. So this is nothing but this is one of the very classical example of optimization. So if we go by the definition of optimization, so in mathematics, computer science, economics, or management science, where we are applying this optimization tool, it may be referred as the selection of the best alternative with regard to best alternative with regard to some desired criteria. Of course, this is with respect to from the available set of alternatives. Okay, so in very simple words, we can decide upon that what route will be best suited under the given conditions. So that is how we define optimizations. So in optimizations, we have certain number of solutions, among which we have to select the best solution depending upon the certain criteria. So in this way, we can define what is optimization. Optimize means to make or design something as perfect or as effective as possible. Certain examples of optimization are designing of an airplane. So that is also a classical example of optimization. We are designing the wing in such a way that will increase the lift and reduce the drag. So that is basically the criteria, and on that basis, we are proposing a optimum design. Though there are many designs, but the optimum design is the one. Say, for example, if my criteria is minimum drag, maximum lift, so that is the desired criteria on which we are designing an aircraft plane. So this is how we can define optimization in a very simple words. Now, just to give you an example, say if we have, so the example is something like this, an open top serving box will be made. So this is basically a cardboard, a rectangular cardboard, from which we wish to make an open box. Okay, so serving box will be made by cutting squares out of each corner of 12 by 18. So this is basically 12. The height of this or the width of this cardboard is 12, and the length of this cardboard is say 18. So a box we can make by cutting out these edges from all the four corners. And then we will be folding up these edges to transform this shape into a box. Now, the question here is, what will be the value of this X so that the box which we are making, the volume of that box is maximum? So this is really an optimization problem. Now, how to solve it? So what we do in the classical techniques of optimization, all of us are familiar with the simplex method and some of the I can say pertinent cases of simplex like transportation, assignment. So this is one category by which we are solving some of the optimization problems. Then at times we will be using the concept of derivatives to solve any optimization problem. So here we will use that particular concept to find out what will be the value of x so that the box, the volume of that box is maximized. So an important, how we can formulate this problem? So volume is nothing but length, breadth into height. So if I say the dimension of the corners which are to be cut out is x, then the length will be 18 minus 2x, the width will be 12 minus 2x, and the height of that box will be x. So this is the volume. Now, if we wish to maximize this volume, what I can do, I can find out the derivative of this volume with respect to x and equate it to 0. So if we do this, we can go for the maximum volume also and for the minimum volume also, because for minima and maxima criteria, the first derivative should be equal to 0. So if I just solve this equation and I put the first derivative, so this is the volume upon solving these or multiplying these three terms, and then we will be differentiating this dv by dx. So once we differentiate it and we put it equal to 0, we will be getting a quadratic equation, and finally we will be getting two values of x. One is x comes out to be 2.35, and the second value of x comes out to be 7.65. 7.65 is an ambiguous value, because if we just subtract 7.65 2 times 12, this will be negative. So this is not a feasible value. So the value of x, that is 2.35, is such value at which we will be either getting the maximum volume of this box or minimum volume of this box. Now, to confirm whether we are getting maximum volume or minimum volume, what we'll do, we'll see the sign of the second derivative. If the sign of the second derivative is negative, what we will get is maxima. If the sign of the second derivative is say positive, we will get the minimum value. So if we just see here, the sign of the second derivative, we will be getting negative here. So once it is negative, that means whatever value we will get for x, that will give us the maximum volume of the box. So x is, when x will be equal to 2.35, so this will give us the maximum volume of this particular box, which we have just cut out from a rectangular piece of cardboard. So this is one such technique by which we are solving the optimization problems, that is putting the derivative equal to 0. So this is, we are using the calculus to solve optimization problems. And at times we will be using a very simple method, what we call as a simplex method. Then there are some subset of simplex method, like a special case of simplex is transportation, assignment. Then at times in nonlinear programming also, we will be using this the process of optimization to find out the different values of the variables. So generally in engineering, we are practicing these kind of things to find out an optimal solution to any given set of problem. Now, if we see the classification of various algorithms, though the classification is quite large, but this is a very broad classification. We can divide all the methods into two categories. One is what we call as exact methods, and the second category of the methods, what we call as the approximate methods. The name itself suggests. In exact methods, we are specifically getting a very precise value. Okay. Say the optimum should come out at x equal to 2. So once we solve it, the value of x will come out to be exactly 2. But when we solve it with the help of approximate method, it may come very close to 2. Say, for example, 1.99 or 2.01. like that. So that is basically the difference between exact methods and approximate methods. Now, though we prefer exact methods because they give us, of course, the exact values of the different variables, but at times we have to do a trade-off, because if we go for exact method, it may take a lot of time for computing those values. However, we can get an approximate value with less time interval or less computational time. So that is, sometimes we prefer these approximate methods over exact methods because of the computational time. Now, again, in this exact methods, we have iterative methods. A very classical example of iterative method is the, we can say, simplex methods. First iteration, we are finding out the basis, and then some variables we will be dropping and new values are coming in. So we iterate towards the best value. Sometimes we go for enumeration. Enumeration means we assume certain solution and then we improve upon this solution towards optimality. So this is the classification of the exact methods. Now, approximate methods, they are further divided into two categories, what we call as heuristics, and another set of methods, what we call as meta-heuristics. Heuristics is simply when we are designing any optimization method for a specific problem. So this algorithm may not work if we change the problem. So we call this as heuristics. That means designing a tool or an optimization technique for a specific problem. However, in meta-heuristics, we design algorithms, and this algorithm is used not just for a single problem, but multiple problems can be solved with the help of an algorithm under this meta-heuristics category. So as far as genetic algorithms are concerned, although we have certain algorithms which are heuristic in nature, we can program that particular algorithm just for a specific problem. However, in real sense, all these evolutionary algorithms or genetic algorithms, they fall under the category of meta-heuristics. That means the same algorithm can be used to tackle a problem of aerodynamics. The same can be used to solve a problem related to assignment of machines. So genetic algorithms, the beauty of genetic algorithms lies here, that this belongs to the class of meta-heuristics. That means the same algorithm we can use in a variety of problems. Now, coming on to genetic or evolutionary algorithms, sometimes these all names are synonymous or they can be used interchangeably. Either we call this as evolutionary algorithm, at times they are called as genetic algorithms, or sometimes we may use another term, what we call as nature-inspired algorithms. So all these things, all these terms basically convey the same meaning. So evolutionary algorithms are a subset of evolutionary computations which are generic population-based meta-heuristic optimization algorithms. The first thing is that these algorithms, they are used for optimization. Second thing is they are meta-heuristics in nature. That is, if we program a certain algorithm, then the same program we can use in a variety of problems, but just by manipulating few things. We will see what things we can manipulate when we switch over from one problem to another. And of course, this evolutionary or genetic algorithms, they are based on some population set. Here, the population set is nothing but every member of that particular population is basically a solution to the problem for which we are modeling. Okay, so important features. First thing is that they are meta-heuristic in nature. The second thing is that whenever we are making computations, these computations are population based, where each member within that particular population represents one possible solution to the problem. The basic idea behind this evolutionary algorithm is that once we create a population, then what happens in real life, the population pool changes from one time frame to another. The same thing is happening here. The population set is changing with respect to time. And how it is changing? It is changing because of the fact that only those members will survive which is having higher probability of fitness over others. So that is the basic criteria, and that criteria is basically based on the Darwin's theory of survival, which simply states that the survival of the fittest. So when one generation of population is changing into the second generation, the members which are not fit for that particular solution, they die out, and a new population set is created with the help of the surviving members. Of course, the surviving members, they have better fitness values over the members, those who have died out. So that is the basic philosophy of developing any evolutionary or any genetic algorithm. So here, if you see, I have already mentioned that we create a population, then every member within that population basically represents a set of solutions. Okay. Now, how we judge that which set of solution is better over the other? So this we can determine by a term what we call as a fitness value. Okay, so in our family tree, some of the members, they are better over others in terms of some aspect. Okay, so whatever the aspect is, so that aspect can be defined with the help of a fitness function. Okay, so we will see how we can incorporate this philosophy in designing any evolutionary algorithm. So that is all about genetic algorithms or nature-inspired algorithms, because this is the law of nature, and we are trying to implement or to use this particular law in designing any algorithm. So an evolutionary algorithm uses mechanism inspired by biological.
Am I audible?
Yes, you are audible. Yes, you are audible.
Okay. So any biological event. So what we are trying to do in this, we are trying to replicate a biological phenomenon. So biological phenomena related to how generations move from one time frame to another, or how population changes from one time frame to another. So when we talk of biological evaluation, these are the features of biological evaluation. That is, one can reproduce in biological evaluation, one can mutate, one can recombine or crossovers. So these are some of the characteristics like reproduction, mutation, crossover, and selection. So we will see how these terms, they are incorporated when we are trying to develop any algorithm which is based on such evolution. Okay, because if we see within any generation, we have n number of members, but every member is having a different color, a different build, different color of eyes, different color of hairs. The physique is different. Some are male, some are females. So the basic thing lies here, that every person is having a unique gene, and that is basically differentiating one family member from another. So we'll try to incorporate this kind of phenomena in developing an algorithm, and any such algorithm developed, we call this as a genetic algorithm. So In order to develop this phenomena, genetic operators are applied to select individuals in order to produce new individuals. So I have already told you that the family members within a generation, those who are having weak fitness value, they will die out, and new set of population will be created with the help of the process of reproduction. Now, whenever reproduction is there, we have to choose the members from which this reproduction has to be there. So that is basically the selecting of individuals who will take part in this particular process. So that will be one such thing that will be incorporated in this algorithm so that new better solutions are created from the old ones. And finally, these solutions keep on improving until unless we will get or we will achieve the desired criteria of terminating this process or this cycle. Okay, because this process will go on, because population cycle, it keeps on going, and we are evolving say, for example, if we have evolved from the early we can say we evolved to Homo sapiens from what we call as from primitive age. So this is basically the process of evolution. So the thing is, we have to stop somewhere so that we can get a solution. Otherwise, this will keep on improving. But the improvement in terms of time will be very less. So we have to select a criteria at which we will be stopping this reproduction process, and whatever we are getting in the form of solution, that is basically the solution to that particular problem for which we are designing this algorithm. So new individuals, whenever we create new individuals, that are also evaluated on the basis of fitness function. And again, the same process is repeated. Now within this new population set, those members who are having poor fitness as compared to others, they will die out, and new population set is created, and this cycle keeps on going until unless we achieve an optimal solution, and based on the termination criteria which we have, for which we have programmed our genetic algorithm. So that is the basic philosophy of programming or modeling any genetic algorithm. So evolutionary algorithms, this is another division on the basis of which we can classify various algorithms like evolutionary strategies, evolutionary programming, genetic algorithm. And what is the difference between all these is that how we are basically selecting the members for generating a new set of population, and how we are evaluating the fitness function. So we will see how, because within this evolutionary algorithms, we have different algorithms, like the common name which you have heard is, say, ant colony optimization, you have heard particle swarm optimization. So all these algorithms, they are genetic algorithms. But what is the difference between the two is how we are selecting the parents for reproduction and how we are carrying out other phenomena pertaining to crossover and mutation. So that selection, representation, and the usage of operators, it differs one algorithm from another. Like in ACO, we are having a different selection procedure, different method for crossover and mutation. On the other hand, if we are using the particle swarm optimization, it is having a different methodology of selecting the parents and then going for crossover and mutations. So the thing is that in all the algorithms, there are n number of algorithms under this category, what we call as genetic algorithm. The difference between all the algorithms is that what criteria we are using for selecting the parents and what criteria we are using to go for mutation and crossover. So these things differentiate one algorithm from the other. So directed search algorithm based on the mechanism of biological evaluation. So this figure clearly explains that how the human race has evolved over a period of time. Now, every time from when one generation is being succeeded by another, we are having some improvement. So that is basically depicted by this particular figure. You see, earlier we are moving with the help of 4 limbs, then earlier only 2, and then there is certain improvement in the postures, and rather than if we progress, we are having something which is more technology enabled, better human beings with respect to many criteria. So this is what we need to program in order to have any genetic algorithm designed for a specific problem. So that is what we need to program, or that is what we need to model. And of course, the basis of all this is the survival for the fittest. So this is how we go for the modeling of any algorithm. Now let us see whatever we have discussed, how to model it for certain specific problems. So just moving ahead, just see some phenomena. You see, this is a very common phenomena. We have seen the ant colonies, and when you notice the movement of these ants from, say, for example, this is nest and this is food. So of course, even in our household, we will find many ants moving from one place to another. But have we ever noticed that whenever these ants, they are moving in large groups, they always follow same path? This we all have noticed. Majority of the ants, they follow the same path. Now, another important thing which is noteworthy to mention here, that say from nest to food, these ants, majority of the ants, the path which they follow is the path with the minimum distance. So that is another thing which humans have large brains, so they can see, they can evaluate that which path is best suited for them under the given circumstances. But when it comes to ant, they are having some genetic code in them which enables them to select the shortest path between the nest and the food. So this is something which is in their genes. Now, if we model this thing for some specific problem, then of course we can call this as a genetic algorithm, because this algorithm is inspired by the genes which are present in ants. Okay, so this I have shown with the help of pictures. So from this is nest, this is food, and these are the several paths. So initially what happens in the beginning, you will find these ants are spread over to all the paths. But with the passage of time, you will see the movement. Majority of the ants, they will move on the same path. So one thing is they all move on the same path, and this is the path which is having a minimum distance from their nest to the point where food is available. So this kind of thing, if we incorporate this kind of thing in the algorithms, then of course this algorithm will be termed as a genetic algorithm. Specifically, if we work on this is called as ant colony optimization, ACO. So this is one such examples by which nature inspired us to think over it and to program this algorithm for meeting out the solution to different problems. So this is another example which is quite visible. Birds moving in a flock or in a swarm. So one bird is leading and rest of the birds, they are following. So this we generally see. But another phenomena which one can see if we keep a track on this over a long period of time. Gradually, over a period of time, the first bird which is leading this formation, this bird will shift here and another bird will be occupying the same position. So what is this phenomena? This phenomena is basically when they move in such formation, this will reduce the effort in their movement, or this will reduce the expenditure of energy in flapping of wings. So this will reduce the drag on them, and this will increase the lift if the birds they move in this formation rather than moving alone. So this is also something which is nature inspired. So we can use this basic philosophy in making algorithms for the solution of certain class of problems. Now here also, if you just compare, there is something which is in their genes which automatically forces or which automatically make these birds intelligent enough to move in this formation. Okay, so this is another what we call as to some extent we can model this, and the name for this is particle swarm optimization. Even this is true when certain birds they are basically moving in on an ocean also. So this is another genetic algorithm. The specific name to this algorithm is what we call as particle swarm optimization. So all these algorithms, we can model these algorithms with the help of computer programming languages for solving any given problem, optimization problem. Now let us see how we can model this. So that is the basic idea behind this presentation. So to begin with, you see the most sophisticated program which is around us is the code which is there in our genes. So this is what Bill Gates has said in the year 1994, and even this is valid today. This is the most complicated program which is around us. That is the what we call as a programming behind gene, because it is only the gene which makes us differentiable from a fish, or fish, we can differentiate a fish from an animal, deer, or a deer is differentiable from an eagle. So the difference is only in the coding of gene, which makes us as a human being, which makes us this particular a fish, this particular a deer with running capability, with swimming capability, and with flying capability. That is all because of the code which is there in our genes. So that is why gene is considered to be the most sophisticated program around us. Now what we have to do, we have to somehow code this gene. Of course, when we are coding this gene, so this gene will be for a specific problem, and you change the gene value, the same gene can be used for a different class of problems. So the thing is, to begin with, first of all, what we need to code a gene. Whatever problem we are having, you just code a gene for it. And when you switch over to another problem, the same algorithm is used, but now the gene will be different. Same algorithm, but the gene value will be different. So that is why we call this as meta-heuristics. So these are the basic steps which are there in programming any genetic algorithm. First and the most important thing is the coding. Coding of what? Coding and representation of the gene. Because here population is basically defined by the genes, because there are different members within a population set and each member is having a different gene. Okay, So coding and representation is the first thing, and sometimes it is often complex. So once we have a coding and representation, then 50% of the genetic problem is solved. The problem lies here is how to code it and how to represent it.
Faisal Saab, we can't hear you. You are not audible. Dr. Faisal, can you hear me?
Am I audible? Am I
You're
audible?
now. Yeah, we lost you for some moments, but you are back now. Yeah.
Okay. Okay. So perhaps you have heard me on this slide.
Yes, we have. Yeah.
Okay. So the first thing is the coding and representation. So that is, I have already told you, that is the most critical thing whenever we are going for making any genetic algorithm. So I'll give you some examples of how to code and represent the same. Then of course, I have already told you, so this coding and representation, it helps us to create family members or population members, we can say. So sometimes this coding and representation, it is also known as the initialization of population, because the basic thing is we create a population, and then from this population set, we evaluate each of the member within this population set. Then the members having lower fitness value, they will die out, and in this way the new population set will be created, and so on. The process keeps on repeating until unless we give some stoppage criteria. So the first thing is coding and representation, and this is nothing but this is what we call as the initialization of population. Just hold on. Okay. The second thing is, once we create this population set, we need to evaluate the fitness of each member within this population set. We call this as evaluation. So for every problem, we will be having a fitness function. So at times, if we don't have a fitness function, then we need to define a fitness function. Like for example, if you take up a problem of say simplex algorithm, then whatever function you need to maximize or minimize, that is nothing but that is the fitness function. But at times we need to create a fitness function, because until unless we don't have a fitness function, we can't tell that which member within a given population set needs to go ahead and which one is to be died out. So the thing is, we need a fitness function. So at times the fitness function is simple or relatively simple in the sense that it is given in the problem. But at times we need to formulate it. Then once a fitness function is formulated, then based on this fitness function, some members, they are having good fitness value, some are having poor fitness value. So generally, those members who are having poor fitness value, we don't expect them to take part in the reproduction process or generating of offsprings. So generally, those members which are having higher fitness value, higher probability should be assigned to those members, so that for taking part in the process of producing offsprings. So that is what we call as reproduction or generation of offspring. So those members which are having better fitness value, they will take part in this process, And in this, a new population set will be created. Now, in this, we applied certain, what we can say, genetic algebra, we can say. We can apply this, some certain genetic algebra on this new population, so that within this population set, we can model two things. One is crossover and another one is mutation. So a lot of things you have heard over these days regarding mutation of this COVID virus. So that is basically a natural phenomena, and this we have to take into account in this case also. That is, once a population set is generated, then the genes which are transferred from parents, so there is a possibility that the genes will be transferred from parents to offspring, but there might be certain gene which is entirely new to this new set of populations. So that we can do with the help of mutation or crossover. So we'll see how. And finally, we have to define a criteria to stop this program, because since this is based on biological evaluation, so it will continue. But we have to define certain time frame, a certain number of generations for which these programs we need to run, and after that we will be able to get the results. Because if we optimize towards optimality, and even if we are going for an approximate solution, so initially the convergence is fast, but later on the convergence is very slow, say 1.99. So after 200 iterations, you will get 1.999, say for example. So after 1000 iteration, if this is the change and the value we need 2, so it's better to stop it at 1.99 without going or without spending time on 1000 generation. That is the computation time for these 1000 generations. We can save that. Okay, so the convergence needs to be defined. So this is how we program it. Says, first of all, initialize population, then evaluate populations, these two functions we have created. And the thing is, for every population set, we will be, when the termination criteria is not satisfied, we will reproducing the offsprings, evaluating them, dropping off the members which are having poor fitness value, and the same iterative process is being repeated until unless we meet the specific termination criteria. So this is how we program it. A simple program, we can say, you first of all, you have to initialize something, then you have to evaluate, and then this cycle needs to be repeated over some pre-specified criteria. So this is what we call as a simple GA. Simple GA because we are not incorporating many things in that we'll discuss in some of the slides later on. Now, initialization. So if we see initialization, an individual is characterized by a set of parameters gene. So I am different from rest of my family members. That is just
Dr. Hasan, we have lost you. I think there's some internet problem at Dr. Hasan's side. He might be fixing it. I think there is a loss of power there. We'll have to wait for a few minutes and hopefully he'll join us again.
please let me know.
Yeah, Faisal, Hasan, you are back
okay.
now.
Okay, I'm back now. So this is how we initialize. That is what we are trying to create. We are trying to create a population set. Of course, within this population set, we will be having certain members. Now, one member is different from another, and the basis of this difference lies in the gene. Okay, so the thing is that any human being is basically composed, is having a gene value, and different genes are combined together to create a chromosome. Now, I am having my own chromosomes, and rest of the family members, they are having their own chromosomes. So I am different from them. So this is basically at a primary level, it is gene, but combination of gene will give rise to chromosome. Or we can say that every chromosome of one family member is different from another family. So the chain is like this. We have a gene, then for putting many genes together, we lead to a chromosome. With the help of a chromosome, we will get a genotype. We'll see what do we mean by a genotype. And from this genotype, we will be getting a phenotype. Okay. So the thing is, first of all, we have gene like cell. Cell is the building block, electron, proton, neutron. Then above that, there is a, we can say, atom. An atom leads to molecule, molecule to material, like that. So here we have the hierarchy gene. Gene will lead to chromosome, chromosomes will lead to genotype, genotype will lead to phenotype. So this is the hierarchy. Let us see what's the difference between all these. So this is a classical example of representation of a chromosome. Now, if you see what I have a 8-digit binary code. Of course, some digits are 0, some are 1. So this is what we call a chromosome, and every digit we can say that this is a gene value. So this is a 0 is a gene value at this particular place, at the 4th place. 1 is the gene value at the 1st place. And all these genes, they are put up together to form a chromosome. So this gene, it may be binary in this case, because 0 and 1, 2 are the possible values. It may be integer also. It may be any other thing. It depends upon what kind of problem we are taking up. I'll explain with the help of some examples also. So here, just think that chromosome is nothing, but it is having a set of, say, genes which are combined together. So this may be in the form of binary numbers, this may be in the form of real numbers, integers, or whatever. It may be in the form of some alphanumeric value as well. So it depends upon the type of problem which you are taking up. So that is why I have told you that this is the most important and the most complicated thing of converting the problem into a gene related problem. Now, once we have this gene, what we can do, we can create a population set. Okay, that is the very first step. Now you see, if this is the population set, every member is different. Why they are different? Because the coding at the chromosome level is different. So the type of chromosome, binary, we have seen. So again, this is a kind of chromosome. We may have a real coded chromosome also, and we have a permutation type chromosome. Say, for example, if I have 10 different cities, so I have assigned, say, New York is city 1, then Belgium, say, Moscow is city 2, New Delhi is city 3. So 1, 2, 3, 5, this I can arrange like this. So this is what we call as a permutation type. So coding of chromosome depends upon the kind of problem for which we are making that particular code. Okay, because the program remains the same. If you are switching from one problem to another, the program remains the same, but what you have to do, you have to change the coding of the chromosome. So the same program fits in to a second variety of problem. Now let's see here. Like, we call this chromosome as a genotype, because when we are talking this at a gene level, this is what we call as a genotype. So either we call it as a chromosome. Chromosome is a we can say biological term, but the same can be we can call as a genotype as well. So genotype, it originates from the word gene, gene type. Gene type is basically genotype. So here a genotype may be integer. So 0, 1, 2, 3, 4 integer. It may be binary 1, 2, 3, 0, 1, 0, 1, 1, 1, 0 like thing. It may be a schedule. It may be a permutation of numbers. It may be real numbers. So this thing is what we call as a genotype. Now let's see how we can generate this phenotype out of this. Like this is a genotype. Now if I just apply the conversion of binary into real, so we can convert this information like this. Okay. So what value we get is 163. Converting this binary numbers into real numbers. So what we get is 163. Now 163 is a phenotype of this genotype. Okay. So that is the difference, because the same thing we can code that will give us different values. Okay. So if I am decoding this genotype on the basis of conversion of binary into real, this will be the phenotype. But if I convert this, say for example, if I just convert this into say a real number between, say, instead of any real number between 2.5 and 20.5 using 8-digit code, so I can convert the same code like this. I can convert the same code like this. Any real number between 2.5 to 20.5. So this thing, the same code can represent this number also, that is 13.96. Instead of representing 163, in this case, the same code can use to represent a real number which is in between 2.5 and 20.5. And now in this case, this is what we call as a phenotype. So the same genotype can lead to different phenotypes. Okay, so it depends upon the type of problem. So at one point of time, and I'm converting this genotype by using the conversion of binary into decimal. So we are getting 256, or into real numbers. Now here we are just converting this into a number which is in between 2.5 and 20.5. So this is formula which we can use. So the same code will give me the value of x as 13.96. So now from the same genotype, I'm creating a different type of phenotype. So this is the difference between genotype and phenotype. Now the phenotype is 13.96. Now this thing can also represent some other thing also. Like if you see here, say these are the jobs. Okay, so I say 1 stands for a job taking 2 minutes and 0 stands for a job taking 1 minute. So in manufacturing, say for example, if we had 8 different jobs and I want to minimize the time for all these jobs in a batch. So this code I can represent like this, like job number 1, it requires 2 minutes. Job number 2, it requires 1 minute. Job number 3, it requires again 2 minutes because the value is 1. So 1 represents 2 and 0 represents 1, and I have 8 jobs. So this is also a phenotype. Same gene, but different phenotypes. So the thing is that whenever we are creating any initial set of populations, we must ensure what kind of phenotype we need to produce. Okay. At times, if you are dealing with just integers, then no need of conversion to decimal. Your phenotype should not take decimal values into account. If it is a schedule, then it should not take decimal values or some real values into account. So it all depends upon what kind of problem we are modeling with the help of, or we are making a code for what kind of problem. Now, so what we can say as a summary, that basically chromosome or genotype represents a population. It may be a number in the form of bit strings, it may be real numbers, it may be permutation of elements, it may be something like this, or any other structure which you wish to create depending upon your own intelligence, okay, your own thinking. So that is why I said this this makes one genetic code like AND colony algorithm different from PSO. Okay. And PSO from, say, for example, beehive optimization is another technique. So that makes one coding different from the other. So, but at times this is very difficult because one has to think over it, that what kind of information I need to represent or what kind of genotype I will be using for my particular problem. Okay. Any issues till now?
We will take question answers after the lecture.
Okay.
So please continue.
Okay. Now another example, like for example, I have already told you, say for example, if I list, say I need to travel to all these cities. So I may start from London, then I can travel to Dunedin, then Beijing like this, or I may start from London, then go to Venice, Singapore like this. So what for optimizing this now, my criteria is I should travel in that way that will optimize my air distance. Okay. So of course, this is an optimization problem, or simply you can say that this is basically a traveling salesman problem. Now, traveling salesman is a heuristic algorithm. That is, we have a specific algorithm when we are having this kind of problem. That is, we need to travel to different cities, and the objective is to minimize the total transportation distance. Now, can I solve this with the help of genetic algorithm? Yes, of course, I can. Now, the problem here is that first of all, I need to code a chromosome, or I need to have a genotype. What I can do for this, although what I am doing, it will be different from what you are doing. You may have some different different set of parameters on the basis of which you can design a chromosome. Say, I did it in a very simple words. I have assigned some numbers, like 1 represents London, 2 represents Venice, 3, 4 like this. So one chromosome is like this. So I will be traveling to first, I will start from Dunedin, then I will travel to Beijing, then I'll travel to Tokyo, like this. So this is one such. How I am decoding it, though I have used the numbers, but I am decoding it in that way that 3, that is, I'll start from Dunedin, then I'll travel to Beijing. Okay. So this is again a traveling salesman problem, but for the same problem, I'm taking these permutations into account for designing a chromosome. Another chromosome I can model that I'll start from Venice, travel to Beijing, and so on. So you see, we have 2 chromosomes, and rather each chromosome basically is representing one possible set of solution. It's basically representing one possible set of solution. Okay. So I can create many in this set. Instead of 2, I can start from 1. I may start from 8. I may start from 7. And this way I can use different permutations of the same to create many number of chromosomes. Okay. So although we have some fixed number of chromosomes, but we can create, apart from 2, we can create 3, 4, 5, or 6, whatever. Okay. This is one such way. So the thing is, now this is a genotype, but when we are decoding it into a phenotype, it will be like this, that I will be first traveling to Dunedin will be at first, second will be at Beijing, like this. So the thing is, from genotype to phenotype. Okay. However, the same chromosome can be used for modeling a manufacturing system. Like job 1, 3 minutes, job 2, 5 minutes, job 2, 7 minutes, job 4, 2 minutes, like that also. So for the same coding, I am converting the same genotype into different phenotypes. Now let us see an example how we initiate. So let us estimate the optimal values of A and B using GA which satisfy this. Okay. So I need to find out the value of A and B. Of course, A and B should lie between 1 to 10, say for example. Now I need to find out the values of A and B so that this equation is satisfied. Okay. So I have formulated the function in this form. So the function can be written as like this. So that means if I write it in this way, the value of a and b should satisfy that the value of function fab comes out to be 0. Okay, so if I'm writing the same function in this way, the value of a and b, the optimum value of a and b are such which will satisfy that fa comma b comes out to be 0. Okay, fine. So how it starts? It starts from initialization of population. Okay. So it will start from the initialization of population, and once we initialize the values of a and b, we call these as chromosomes. Let us see how. So if I just make a program in simple MATLAB, what I did in this, I generated random numbers starting from 1 to 2. Now first digit will represent a, second digit will represent 9. Okay, so 5 and 9 is one possible set which represents a possible solution to the problem. It may not be optimum, but it may be a possible set. Similarly, second chromosome, third chromosome, fourth, fifth, sixth, like so on and so forth. So randomly, I have picked two numbers between 0 to 1, such that the value at the first place, it represents A, and the value at the second place, it represents B. So these are the possible numbers, but they may not. These numbers, they are not the optimum solution to that particular problem. But randomly I have selected. So this is one such technique by which we can create a set of chromosomes, or we can initialize the population. So essentially, chromosome 1 is one family member, chromosome 2 is second family member, third family, fourth, fifth, sixth, and so on and so forth. So it depends. So the problem is relatively simple. So just two random numbers are generated between 0 to 10, and each one is basically representing a family members, and this from 1 to 6, it represents a population. So initial population is this one. Fine. Okay. Now, once a population is generated, we need to find out that which family members in this population set, they are having a better fitness value over the other. So that is the second step. So for a very simple problem, random number generation will do. Like in this case, random number generation will do. But in some more complex problems, we need to think over it, that how we are generating this pair or this set of chromosomes. Okay. So fitness is very simple. Like, for example, if you set the criteria that among the family members, or the one which is having the best body this height to body mass index value, that is the best one in terms of health, BMI. The one which is having the highest BMI is the best family member. So you calculate the BMI for each family members and you rank them in the decreasing order of BMI. So the member who is at the top, he is the best fit member in your pool of population. Okay. So fitness function we need to define sometimes, but sometimes if the problem is relatively simple, you can it may be given in the problem itself. Like in this problem, if you see here, the fitness function, this same function can be used as a fitness function, because how we define fitness here? We define fitness here that the value of A and B, which will put this function, the value of this function equal to 0, that will be the best family member within that population set. Now you compute, you put A equal to 5 and B equal to 9 and compute what is the value of FAB. So 0 means best, and higher on the side, that is higher maxima, positive value, or higher negative value, they are the worst members. Best is which is close to 0, because you have a function where A and B, 2A square plus B must be equal to 57. Okay. So the thing is, if I write the function in this way and if I put the values of A and B, the best family member is the one which will give the value of this function equal to 0. Now, if you put the values of A and B, you can compute the fitness value. Okay. So why we are calculating the fitness value? To focus the search in promising regions of space. Actually, what happened in any optimization problem, we have a search space. And in this search space, every point basically represents a possible solution. But we need to look where among these possible solutions, the optimal solution is lying. We need to search. So the thing is, in computational method, the best thing is what we call as the hard computation. You will be evaluating all the points. But when we talk of mathematics and we are talking of a search space, we are having infinite number of points. So it is not possible to evaluate each and every point within the search space. So what we try to do, we somehow try to determine the area first, the area within the search space, which is having the high probability of finding an optimal solution. So fitness enables that. Once we calculate the fitness value, it will give us an idea where the solution is lying. That means among this solution, the solution which is close to zero, we can say among these solutions which we have created in the form of random numbers, which is close to zero, is the solution which is close to optimum. So we will search in the vicinity of that. Okay, so this will basically reduce our effort in searching the optimum solution. And why it is reducing the effort? Because now we are localizing on the area where there is a possibility of having an optimum solution. Okay. So this is the depiction. We have a search space, and every point on this is basically representing a solution. But if I say I want to find out the maxima, so this is the ideal point. So if we look here something, that will again, the thing is, we will be consuming of a lot of time and we will be searching our solution. But if we search somehow here, this will reduce our computational time. Okay. Similarly, for the minima, if we search around this thing, we will get a faster or a faster minimum value, or convergence will be faster rather than searching here. So this fitness evaluation, it will basically increase the chances of arriving to an optimum solution in the shortest computation time. Now, this is how we evaluated the same. Say, okay, let me do the first one. So I have given you this example. So I have generated two numbers between 0 to 10. Now, if you find out, if you put A equal to 5 and B equal to 9, and you find out the value of the function, this comes out to be 2. Okay. Similarly, if you put 9 and 7, this comes out to be 112. Similarly, so on and so forth. In this case, though I have written 36, but it is rather minus 36. Okay. So you can check. So these values I am getting. So the thing is that among these chromosomes, for the same problem, if I wish to find out which chromosome or which family member is having the best fitness value. So close to 0, I said close to 0 means best as far as the given population set is concerned. So I can rank these chromosomes. So this is having close to 0. So I rank this as 1. And bigger than 2 is 36, because now we are deviating from 0. Close to 0, the best close to 0 is 2, so rank 1. 36 is second close to 0, so rank 2. So I have ranked all these chromosomes. That means I can simply say that this family member is having the highest fitness value among the all given. Second one is this one. Third one is this one. Fourth one is this one, like so on and so forth. Okay. Now some other examples. Like if you see here, say if this is how I have coded the gene, or this is the genotype, and if I'm converting this with the conversion of binary into decimal, so this is 3, this is 1, this is 6, this is 2. So if I just get the total out of it, so total is 12, minimum value is 1, and say the maximum value is 6. So if I am interested in maximum, so this is the best chromosome. Okay. And the second best chromosome is which one? Which is having next highest value, that is 3, that is 0.25. So the thing is, if I'm going for maximization problem, so I can say that if I have coded the genes like this, I can say that this is the preferred chromosome over the other, or first preference should be given to this one, second preference should be given to this one, third preference is given to this one, and finally the last preference should be given to this one. Now, why this preference is there? This preference is there because we need such chromosomes which we can select among this given set, which can participate in the reproduction process. Because the chances are, if the mating pool is good, the offspring will be much more healthier. So the basic objective here is of calculating the fitness space, because the third step is we have to generate the offsprings. So just to generate the offsprings, we have to see the parents first. So parents can be selected on the basis of fitness function. Those who are having higher fitness value, they must, or our intention should be such that they must take part in the reproduction process rather than any family member which is having the poor fitness value. So if you see here, this is my first preference, this will be the second preference, or this is rank 1, this is rank 2, this is rank 3, and this is rank 4. Now, or I can, sometimes it is quite easy to depict this thing in the form of probability. Why? Because probability is dimensionless. You don't have any dimensions for probability. So simply I can say that instead of rank 1, rank 2, I can assign the probabilities to these numbers. Higher the probability means better are the chances of that family member taking participation in the process of generating offsprings. So how can I assign the probability? I have totaled the same. So the total is coming out to be 12. Now you divide 3 by 12 into 100. So this will give me 3.25. 1 divided by 12 into 100. So this is 0.08. 6 divided by 12.5. Now the thing is, if I look at the probabilities, then higher the probability means higher the chances of survival, higher the chances of selection of this parent into the mating pool. Okay. So that is why the probability, this one is having the highest. So the chances are that this family member should be there in the mating pool as compared to other. Now, if you see, the second best is with the one having a probability of 2.25. So if you see 6, then 110. If I select a mating pool out of this, I will select 110, 110, 110. Second one is 011. Okay, 011. This is the second one. And the third is, say, for example, 0.10. So what I did, one family member is being drawn, which is having the lowest probability of 0.08. Fine. Now, if you see, this is the second pool which is selected from this particular generation, which will take part in the reproduction process. Okay. So from this generation, I have selected certain parents. So I can make these two to generate an offspring. I can make this and this to generate an offspring. I can make this with this to generate an offspring. So different combinations from this I can use to generate my offspring. So that second iteration or second set of population is generated. Okay. So this is one way, or a very simple way of assigning probabilities and selecting best family members from the generation, from this particular generation of population, to select my mating pool, which can take part in the process of producing offsprings. Now, this is basically what we call, in a very simple term, a roulette wheel. Now, what is this roulette wheel? The family member, I have assigned probabilities like this. So the best family member is the third one, which is having a probability of 0.5. So I can design a wheel where the best one is having the highest area, the second one is having the next highest area, the third, fourth, fifth, and so on and so forth. You rotate this roulette wheel, because how come I have selected this parent? Simply, this is a very small pool. So I have selected by just looking at these. But This is my subjective assessment. So assessment should not be subjective. It should be randomized. So how can I make this as randomized? If I assign these probabilities in such a way, and there is a pointer here, and if this wheel is rotated, the possibility of a stoppage of this roulette wheel at this particular point is for the one which is having the highest area, and in this case, the chromosome 3 is having the highest area. Okay, so every time the wheel is rotated, and where it stops, say if it stops here, if it stops here, that means this chromosome is selected. Our objective is to select those chromosomes which are having the high value of fitness function. Chances are, in this roulette wheel, the one which is having the highest area, the selection, the probability of selection is higher for that particular. Rotated, the maximum probability is that third will be selected. The second maximum probability is that one will be selected. So in this, if I want to select, say, 10 parents, you rotate the wheel 10 times. You rotate the wheel 10 times, every time it will be stopping to some criteria, to some number to select that. So in this way, we can randomize our selection. Is that clear? Okay. Yes, organizers, am I audible?
Yes, you are audible. Yeah.
Okay. So this is what we call as selecting the parents from a given population set based on the roulette wheel. So this is one such. You change the selection criteria, you take another one, the algorithm changes. So this is the most simple, what we call as, when we call as a simple genetic algorithm, this is the most simple way in which we can program how we can select the possible parents for producing the offsprings. The same I did here. The one which chromosome is having the highest fitness function, which is close to 0. Now here 2 in this case. So 2 is having the highest. Look at the color. The color of this is same. So if I rotate this, the possibility of stoppage of this roulette wheel is at a point which will, to some extent, it will stop at this particular chromosome value of 1. Second probability is for this one. So whatever the colors are for this rank, the same is here. Now, the thing is, once we select a pool of population, then how many offsprings we need to produce? Because you need to make 2 parents to create an offspring. So this is called the selection of, or tournament selection. So how many number of offsprings are 2? If entirely new, you can convert, or you can change the whole population set. So number of tournaments will be higher. Now, in some cases, what you do, you retain 50% of the parents and 50% of the new population. Okay, so this you can also do. So it depends upon what kind of tournament you are selecting. So a number of tournaments are played just to generate the offsprings. So the chromosome with the highest fitness is selected each time. Larger tournament size, that weak chromosomes are less likely to be selected. So that is the thing. If you go for higher number of tournaments, that means your entire population set will be changed to a new one. Okay. So, but at times, if you are using a different approach, like in some cases, what we call as non-sorting dominating algorithm, NSGA. So in this, what we do, we don't create entirely new population. We retain some of the old population to prevent elitism, and we create few new population set or few offspring, so that the new population is basically a mix of some new members and some old members. Okay, so this depends upon the tournament selection. Now, once we selected any 2 potential chromosomes for taking part in the reproduction process, let us see how the reproduction process takes place in terms of coding. So recombination, sometimes it is also known as a crossover, because now what we have to do, I have to create a new genotype from the mating parents. So how this is created? This is created what we call as recombination or crossover, like see here. So if these are the two parents, these office springs may be created. And if there is a mutation, then what happens, entirely new set or some different chromosomes may be incorporated in the same set of population. We will see how. Like this is chromosome 1, this is chromosome 2. Now if I have a crossover point, so say this is my crossover point, single point crossover. I have only one point from which I need to have a new chromosomes for the office springs. So this is say parent 1, this is parent 2, and this is the chromosome for parent 1, this is the chromosome for parent 2. Now from this I am generating two office springs. So what happens if I am having a single point crossover? What happens? This particular information, which is above this line, dividing line, this will be added to this chromosome, and the same information of this chromosome is added to this. So you see the four colors of these second chromosomes, they are now added to the first chromosome. So we have four different colors which are of parent B. Now they are here, and rest of the coding remains the same. So this is office spring 1. Similarly, the same four codes of this chromosomes are being transferred to this. So if you see match the colors, this is the second office spring which is generated from the two. Somebody has asked me a question. I'll take up the questions afterwards. Okay. So this is what we call as a single point crossover. So in this, if you see, from a mating pool, we have generated two office springs. Now this office spring is having an entirely new gene values or new chromosome, of course, which is some from parent 1 and some from parent 2. Similarly, office spring 2 is created, which is having entirely new information in it. Of course, some information from parent 1 and some information of parent 2. So this is called single point crossover. We may have multi-point crossover. So here we define 2 points. So here I have defined 2 points. Here I have defined 2 points. That is now in between values, like these 4 bits will be interchanged to create the two office springs. Okay. So we may go for single point crossover also, and we may go for multi-point crossover. So of course, if you choose multi-point crossovers, then computational time will be on a bit higher side. Like this one, if I see the same problem, this is chromosome 1. This is now what the problem is with this. Okay, I have selected 2 chromosomes. Now these are the 2 parents which will be producing the office springs. Now see here, parent 1 and parent 2. So this is parent 1, this is parent 2. Now if this is my crossover line, what I did, I say I'm using a crossover from this point onwards to end. So either we can start the crossover from the first point to this line, or I may start the crossover from this point towards the end of the chromosome. Both we can do. Now child 1 is created. So this information remains the same in child 1. And instead of this information is being transferred. So 357 is from parent 1 and 6, 8, 1, 3, 4 is from parent 2. Similarly, another child is created. 257 is from parent 2, and rest of the information is transferred from parent 1, that is 21648. Now what is the problem here? Now if you see, if I have said you that I have assigned different numbers for the cities. Okay, 3 is some city, say for example it is Dunedin. Now if you see this particular child, here one number is vanishing off, and Venice is appearing 2 times, because 3 represents Venice, say for example. So 3 is here, 3 is here. But if you see here in child 1, 2 is not there. 2 is not there in child 1. Similarly, 3 is not there in child 2. So the whole problem gets deviated. Now what the thing is that when we have created a child, there is a solution in which one city is gone and one city is appearing 2 times. So this needs to be prevented, because solution means the constraint is that one has to travel to all the cities. Now if we force on this, otherwise it is iterating towards optimality. It is saying don't travel, stay at one point. So what it will do, this algorithm will convert all these things to a single point, because the optimum solution is distance equal to 0. And how this is possible? You don't travel at all. So though this is iterating towards optimality, but the problem is that the problem for which we are trying to solve, the intention of that problem has gone. Okay, so we need to check. So the thing is, child 1 and child 2 violates the, okay, in this minima maxima criteria. So the thing is, this every solution is to be looked upon. Now how we can look upon to the solution? Now if you see, so this is basically a crossover. Now second operator, genetic operator, is basically mutation. So if I look carefully at this, city 2 is gone. So what I can do, I can add 2 here manually by flipping any of the digit. So 6 may be flipped to 2, because but in that case, if we flip this 6 to 2, then 6 will be gone. So best thing is that 1 3 will be flipped to another number. Okay, so this we can do. Okay, but if I change my crossover point, it may be a condition that I won't be getting the number twice. Okay, like in this case, if you see, 3 same childs are created, 2 6 8, but I have changed the crossover point. So instead of this, if I change the crossover point, I may have a different values. But just to summarize, what we can get, I can flip the digits which are appearing twice here. Okay, so this is basically flipping, means that this, instead of this 3, I can make it this as 2, because 2 is not there, and 3 is not here, so I can flip one of the digit, either this one or this one, with 3. So this flipping of digit is basically what we call as mutation. So mutation is basically, we are trying to see whether the solution is, although it is iterating towards optimality, but certain constraints or certain cities, they are vanishing off. So just to restore those cities, or just to restore those points, I may use the operation of mutation. So the purpose is to take into account the errors that happens with the row probability during duplication. So once we are having duplicate values, so that probability we can reduce by flipping some of the digits. So mutation simply means that one of the gene value is flipped to a different value. And I like this one, like 1001. Okay, 11. Okay, perhaps I have written the same. Okay, let's see this one. Okay, this is flipped. So if you see here, this digit is flipped to a different one, this digit is flipped to a different one. So this is another operator, and this will prevent my solution from deviating from the given set of constraints. Here the given set of constraint is, as far as the traveling salesman problem is concerned, that we need to travel to all points. But when we are coding it with the help of genetic algorithm, you see one of the city is vanishing off, and that needs to be avoided. So the method by which we can avoid this, you look at the new set of chromosomes. If something is happening, you flip that digit with the missing one. So this is essentially what we call as mutation. Like this one. So this is the chromosome. So this has flipped to 6 instead of 7. This is flipped to 6, and instead of this 6, it is flipped to 7. So here we are having 2 cases of mutation, just for example. So this is the chromosome I am getting, but I can flip some of the digits to facilitate the process of mutation. So we have seen that we have generated an initial set of population. Then from this initial set, we have selected potential parents which are having better fitness value. And once we have generated the offsprings with the help of crossovers, then we need to see my solution space again. My every chromosome have to be relooked, whether all the solutions are intact or some of the solutions they are vanishing off, keeping in view the constraint of the problem. So I may use mutation just to facilitate that kind of problem. So this we can do. So mutation can be applied. Like here also, you see mutation is applied. Like this is, say, for example, machine 4. Say instead of 3, this is flipped to 1, depending upon the situation, whatever the problem demands. Similarly, 3 is switched over to 2. So once mutation is, we have incorporated or we have used the operator crossover for producing new offsprings, and we have used the operator of mutation, what do we have? We have a new set of population or new set of offsprings. So in this, again, since you are having a new set, so we need to evaluate the fitness of this new set. Okay, so this fitness of the new set is evaluated again, and the same process is repeated. That is the selection of parents from among this new set, and the one which is having the highest fitness value, that will be selected. And again, the process of third generation will be generated. So we have initial population. Then with this, we have generated first population set. And from this first population set, we will be generating second population set, and fitness we will be evaluating each time. So if we see, or if we just in a program incorporate the average fitness. So in every generation, you will find that the average fitness is improving. So that is, we are iterating towards optimality. Now you fix for how many number of generations you will be running this program. So it may be 50 generations, 100 generations, or 200 generations, whatever. So you stop your program at that particular point of time. So the chromosomes present in those, the one which is having the highest fitness value, that is the possible solution of your problem. And the chances are bright enough that this solution which you are iterating after 100 or 200 generations, that will be very close to the optimum solution. Okay, so I'm just giving some time for question answers. So finally, this is my last slide, that why we are taking up this GA. So the thing is, the concept is very familiar with the biological process. So the understanding is quite clear what we are trying to do. And the beauty of this is, which is not there in case of the linear programming methods, that even you can have multi-objective optimization using this kind of approach. So nowadays, if you see the papers on multi-objective optimization, you will find a large set of researchers using the genetic optimization, because the same program can incorporate the multi-objective criteria also, because you evaluate the fitness. Now you have numerical values of fitness 1, fitness 2, fitness 3, fitness 4. Somehow you integrate it and you evaluate a total fitness function. So multi-objective optimization we can do with the help of same program. Especially this program is good when we have a lot of noise in the data, because even in the first iteration, if you are evaluating the fitness value correctly, then you are reducing your search space. You are focusing on a smaller search space. The possibility is that you will be achieving towards an optimal solution in a very shortest possible time. And the third thing is that if you don't give any or if you run your program for infinite number of time, so it will always iterate towards optimality. Always iterate towards optimality. You don't give any stopping criteria. Whenever you say you program it for infinite loop, and when you want to see the result, you stop the program and then you continue for the same. So better the time, higher the time you give to the program, better the results you will be achieving. So this is the beauty of the genetic programming codes. That is, higher the time you will be giving to the program, the better results you are getting. Of course, the convergence will be slow at the later stages of time, but if you don't have any computational time issues, this will be the preferred one. So this is all about my presentation, and if you are having, I think I am right on time, and if you are having some queries, then I am here to answer that. Please, over to you, Dr. Pankaj.
Thank you so much, sir. Thank you so much. Before the board is open for this discussion, I would like to congratulate you, sir, for this wonderful in-depth talk, which you have. This was really a complex topic, and wonderfully you have explained in a very simplified manner. This actually your not only was technically rich, but it reaffirms this spiritual learning too. In the way, two things actually that reaffirms through your talk. Firstly, was the nature is the best teacher, and the second, the flow of knowledge is from the inner self to the outer world. This was really a wonderful talk, and I would request that all the distinguished participants, they can now raise hands and they can be unmuted so that they can directly interact with you on this. And if they want, they can put their question in the chat box.
So I stopped my presentation first so that I can see the chat box. Okay,
sure, sir. Sure.
Okay, let me see the chat box. Okay. Yes, anyone?
There is one question what's the difference between chromosome and a genotype? So the participant is asking, for example, there was an example of job one where the job has certain time. So what is a chromosome and what is a genotype?
You see, chromosome is a term which we are using for a biological application. Okay, so actually chromosome is combination of many genes. Okay, so but genotype is basically, I have told you, chromosome is something which is unique. But in our problem, what we are doing, we are converting the same chromosome, or we are converting the same chromosome into different phenotypes. So phenotypes we will be getting from genotypes. Genotypes are nothing but another name for chromosomes. Okay, gene, basically genotype is basically is a combination of two words. One is gene and another one is type. So if I am using binary, so genotype is a binary one, but the same binary can be used to obtain a real number and a decimal number. I have already given you an example here. If you see, the same number I have used, the same genotype I have used to create two phenotypes. Ideally speaking, chromosomes and genotypes, they both convey the same meaning. Okay? Is that okay for the participant? Now, okay, Rajkumar, okay, let me take the first one first. Okay. How did we decide the size of the population while solving a GA problem? So this is, I think Mr. Rajkumar Pant has asked me a question. Okay, so you see, larger the, what we are trying to do in optimal. I've already told you that population is basically, every member in the population is basically representing a possible solution to that particular problem. Larger the population means you are taking larger number of points within the search space. Although whenever we are doing an optimization, you see there are two types of optimization. One is hard optimization. If you have a sample space, very small sample space, and you have, say, grid points, okay, limited number of grid points, then the best thing is that you evaluate your solution at all the points. This is what we call as a hard computation. Because here what we are doing, we are not optimizing anything, but we are computing the value of the function at each and every point, and then selecting it which one is maxima and which one is minima. But in optimization, the beauty of optimization is that we don't go for searching at all the points. So the only thing is that it depends upon your computational capability and how many number of points you wish to take within the search space. So that essentially determines your population size. Okay. So it depends upon, because if you take the larger population set, that means your computational effort will increase. If you take 10, computation will be fast. Okay, convergence will be there in 10 also, convergence will be there in 100 also. But when you take up 100, the convergence will be taking a lot of time, because 100 population set is to be evaluated. Okay, so it's always better, whatever your computational capability is, depending upon your processor, depending upon the time you need to spend on computation, accordingly you can decide whether you can take 10 solutions, 20 solutions, or 15 solutions. Okay, there is no hard and fast rule that how many number of family members you need to create. It all depends upon you. You take 10, so iterations, if you take 10, maybe you can run the program for 100 generations. But if you take, say, 200 points, maybe the convergence you will get in 50 generations. So that is the trade-off between the two. Hope I have answered the question, Mr. Rajkumar. Elitism.
Thank you.
Okay. And there is one more question pertaining to elitism.
Thank you, Dr. Pant. First of all, now, so next question is from Abdul Samad sir.
Yeah.
Sir, please carry on with the question, sir. Sir, he would like to know, sir, how do we define twin children by this analysis? Means, how do their chromosomes can be compared with each other?
No, if you are having twin children, actually we don't have a concept of twins in that, because even in twins, twins means if the chromosome value, the two chromosome value are the same, this is eventually twins. So even if the two chromosome values are same, you will be getting the same fitness for the two. Okay, same fitness for the two. So if you are having two same chromosomes in the same population set, the chances are that when you are selecting it, okay, because once you did crossover, then you are doing mutation also. So the chances is that in mutation, if the two chromosomes are same, then one will be flipping. So the chances of having identical twins in the same set of populations is very minimum. Even if it is there, over a set of iterations, one will vanish off, because once you did crossover, so in crossover, you have transferred some of the chromosome information, but I have told you that another operator which we need to apply is the mutation. Mutation is basically preventing all such things, because if you are having two chromosomes same in the population set and the same fitness value they are having, it will be treated as one chromosome. Okay, it will be treated as one chromosome. So 5 and 6 say chromosomes are same, rather they will be treated as only one chromosome. Okay, getting my point? And if you just iterate it for the population set, first of all, when you operate mutation operator, these two chromosomes will automatically get deferred. Okay, and even then, if it is there in the population set, if you keep on iterating, a possibility of one chromosome vanishing off will be there. Or what we can do, or what is there when we are programming it, we keep a check. Whenever we are generating a population, we keep a check that no identical member should be created. No identical member should be created. Once we are creating a random numbers, we will ensure that no two identical strings are produced. Okay, because in twins in chromosome is having no significance. It will be treated as single family member. Okay.
Thank you so much, sir. Okay. I now, as the next speaker has already joined, I would like to request the distinguished participants. They can directly contact Dr. Fasial Hasan, sir. They can have their email IDs from the web server of Aligarh Muslim University. And I request, sir, also please settle the queries
sure.
when.
Sure.
And I'm really thankful to Dr. Fasial Hasan, sir, for this really wonderful talk. The participants also got benefited, and they are really actually in discussion with you. And this was really a wonderful talk. And from organizer's side, I would like to say a deep thanks to you, sir, and to all the participants for this wonderful interaction and kindness. Thank you so much, sir. Thank you again.
Thanks a lot. It's my pleasure to be with you this morning, and I hope you might have got some insight from my lecture, which will be beneficial for your different kind of works which you are taking up. Thanks a lot. Thanks a lot.
Certainly, yes, sir. Certainly. Thank you, sir. Thank you.
Thank you. Thanks a lot.
Thank you, Dr. Faisal.
Okay.
So
Thanks a lot.
with this we have finished our first session.